I'm afraid I learned that from her.
You were much more gracious than she.
Well, that's how she got where she went.
A beautiful condo overlooking the beach on Waikiki? Yeah, I suppose.
Get it done there.
What? Oh, well, I guess I would start with an apology. I wrote this last weekend kind of in a hurry, fueled by 3 cans of Monster Energy, and there are a few mistakes in it. I'll revise and fix the mistakes, and I'll post this on our website. I'll also zip up the source code that goes with it, so it's just one package that you can grab.
Does anyone not have a handout?
There's more than enough, I think. This was actually based on a handout I did a couple years ago, so if the first few pages seem hauntingly familiar, they are. I thought that was a good place to start. The hardest part about writing something is that blank sheet you're faced with, so I started with something I had. Kevin always asks me to talk about a project we're doing, and I never can because almost everything we do is covered by NDA or proprietary. So, at the risk of being sued, or in the case of government agencies going to jail, I usually can't talk about these things. This was funded by NASA, so I actually have permission to talk about what we did for them. We have a, sorry, and this is the best I can do. If I look up and project, does that help? Okay, I'll do my best. I'm a little hoarse. I just came from British Columbia where it was raining and snowing and sleeting all week.
You were hoarse last fourth day, too.
I was, wasn't I? Was it for the same reason? Did I pick up some laryngitis there? Because I came back from there last time, too. We have a whole family of cross-compilers called SwiftX, which is based on SwiftForth, which is our Windows and Linux and OS X Forth. And one of the most popular ones is the one that runs on the Freescale Coldfire. And one of the engineers at NASA got interested in this because he has been trying for a long time to instantiate a CPU core inside an FPGA so that they can use a rad-hard FPGA and get their part count down. You know what I'm talking about, right?
You're talking about being able to program FPGA
Yes.
with Forth.
I'm talking about putting a CPU inside the FPGA that will run Forth. Yes, there are CPUs that do that. For example, Dr. Ting has done several. One of them, I believe he did for this same group at NASA. Unfortunately, there was no buy-in from anybody else at NASA, and they won't use it. But folks at NASA know and love the Coldfire. So this guy thought, well, if I could just get a Coldfire and put it inside an FPGA, I will be good to go, and I'll get some buy-in. And sure enough, he did, and he got funding to do it. At the same time, this wonderful company called IP Extreme came out with this Coldfire core, or a series of Coldfire cores. Is Blagoya here? Nice to meet you. Blagoya is from IP Extreme, the company that makes the Coldfire core that I'm talking about. So they got the Coldfire core and wrapped it all up and actually put it on an FPGA, and it didn't work. So he contacted me, the guy at NASA contacted me, and had me come out and spend a week with him, and together, with Blagoya's help, we figured out all the various loose pieces that needed to be tied together, and we actually got the thing running. I've been working with people who've been doing FPGA designs as part of their systems for years, and to me, it's a dark art. I don't do FPGA designs. I've never done one. And I watched Robin at NASA working with these tools, and I thought, hey, I could do that. And then I thought, well, if I could actually start from scratch and go get the pieces, never having done this, and walk through it from beginning to end with a little help, or a lot of help, and then write that up, then anybody can do it, right? No? Who said no? So that's what I'm going to show you today. I'm just going to show you that whole procedure from beginning to end. We're going to start with a blank project. We're going to add the pieces to it. We're going to connect them together. And then at the end, we're going to drop the fourth in, and we're going to bring it up, and we're going to run fourth on it. There might not be enough time to do that, so I actually have one already done. We can jump ahead to it, but I really want to show the whole thing from the beginning. Okay? Ready? The IP Extreme core that's available for free is already packaged up to run on an Altera Cyclone 3. And you can get a really nice little Altera Cyclone 3 starter kit for $199 from DigiKey. So this is basically all you have to spend anything on. And you can get the development environment, which is Quartus 2, web edition, free, for download from Altera. You can get the evaluation version of SwiftX for free. And actually, the current release doesn't have it, but the next release will have this project packaged up as part of it. And that should happen in the next couple weeks. So basically, just for the cost of the hardware, you can do your entire FPGA design and have this thing running on it, which I thought was kind of cool. So we'll start with an empty Quartus 2. As I go along doing this, if you have any questions, just jump in and ask them, because I think it will be easier to answer them as we go instead of trying to backtrack. And there are a couple points here where we have to wait for Quartus to do stuff, one of which takes 6 minutes. So that'll be a great time to put some questions in.
Can everyone see the screen okay, or should we turn
You
it
know,
to something
the
else?
screen resolution is really fat on this, and I'm not sure all this is actually going to fit on the screen.
You can change the resolution. The projector will.
No, it's the PC has changed its resolution to match the projector, unfortunately.
No, you can tell your
Oh?
PC to crank up the resolution, and the projector will adjust.
Let's try it, because
So
I
what
would
you're
sure love to
saying
see a
is
lot
it's
more.
Too smart for its own good.
Yeah.
That may be a bit much.
16.8, well, that's what it wants to be, but what do you think?
Oh, try it. What's the worst that could happen?
Well, the worst that could happen is it goes, that. Hey, did it do it? Or is it moving
It's
everything?
adjusting. Just be patient. Just click no.
Yeah, but look what it's doing. It's trying to follow me. The projector's trying to follow me. Yeah. Yeah, so now it's just windowing it, moving it around.
So that's the worst that could happen.
Yeah.
Right there.
I want to go back?
Yeah.
All right.
Go back a little.
Well, it went to 800 by 600. Let's try 1020.
1024 by 768 is for sissies.
It
It's
should
fine.
be. Yeah. Well, that's okay. All right. Let's get Quartus 2 back up here. No, see, it's doing it again. Can you see the right edge? Yeah. Do you see my pointer? I can't see from here. Okay, that's good. Yeah, we better leave the lights off. Okay, so the first thing we're going to do, I'm actually going to take my first project and move it out of the way. Ugh, everything is resized. Sorry. I did this on a projector yesterday, but this is the one that actually works. I'm just going to rename it to something else for now. And then we'll go in and we'll make one. So in Quartus, we're going to start a brand new project. So the first thing we're going to do is we're going to go to the new project wizard. The wizard's going to help us. One thing you're going to notice here, the FPGA part and the tools are enormous. You know, it's huge, huge, huge. And then when you get to the end and you get to the fourth part's really small and really simple and really clean, as it should be. Okay, so we're going to name our new project CFV1 for Coldfire V1. Oops, sorry. You have to keep doing this over and over. I'm going to call the top level CFV1 underscore top. That's sort of a convention people like to use. And I'll say yes. And we have to start by adding some files to it. And this is a good time to go and gather up all the files that we already know we're going to need, which consists of all the stuff in this directory, CFE1 Core Altera unconfigurable. And this is the part that IP Extreme distributes. So we're going to go in there, and we're going to go into their source directory, and we're going to pick up the top level wrapper file. This is all encoded Verilog. Is that the right word? Encrypted Verilog. Yes. This one isn't, but everything below it is. Okay. So we're just going to start with this one. There's a faster way to do this, Blagoya. Jump in and tell me. Oops. No. how did I get here? Oh, okay, good. I remembered. No. Sorry, I'm lost. Altera, core, source. We need both of the contents of both of these directories. The fastest way to do it is just select them all. Atom, one more. It's stuck here. And my apologies, this part's a little bit tedious, but we'll get cranking in a minute when we get into the SOPC builder. I think that's all. So we'll say next. The other thing we want to know is what kind of part we're building for, and it defaults to a Stratix 2, but we're going to go down and make this be a Cyclone 3, which is a nice, small, cheap part. And we'll filter this down a little bit. It's a 324-pin FPGA, and we've got a nice fast one. It's a speed grade 6, and here it is. It's that part. So we're going to say I'm going to target everything to use this part. And it's good to do this step now because then a lot of the decisions you don't need to make later on because they'll just be filtered out for you. So there's that. And I think that's all we need to do. I'm not going to use any special tools because I'm cheap and I'm using the free ones. Okay, that's that. Now our basic structure is set up for the project. We're going to use the, I'm going to make sure I'm following my own script here. Yep. We're going to use the SOPC, System on a Programmable Chip Builder tool, to actually build all the components in. Takes a little while to start up. And the first thing you have to do is give the name of project, and I'm going to give it the same name, CFE1_top, so that everything ties together. We're going to have it blast up Verilog to go with everything else. And so here's the blank SOPC builder. This pane under here is we are going to add all the components. We're going to put in a CPU core, just one for now. We're going to put in a PLL so we have some clocks. We're going to put in 2 blocks of memory, one to simulate ROM to boot from, one to simulate RAM to put all our data space and stacks in, and a little bit of downloadable code. We're going to put in a timer because it's nice to be able to time things. And we're going to put in a PIO, parallel I/O, because we have some I/O on this board. We have some LEDs, and you know I like LEDs if you saw my Morse code demo a couple years ago. And there's some push buttons on here too, although I'm not actually going to use them in the demo. We can actually read them in. So the first thing we want to do is add a processor. So here on the list is IP Extreme processors. If that's not in the list, you actually have to add it once, but I've already done that. So we're going to say add. And then it plays dead for a while. We wait, we wait. There it comes. Okay. And we see that, in fact, this is the module that's going to be added. There's just this nice block diagram. Now, if you had the configurable version, you see these little things in here that are grayed out? You could actually configure those, but they're pre-configured for us, and they're perfectly fine selections for what we're going to do. We'll come back to this in a moment. Let's just get all the pieces on here first. So let's put a PLL on here. This is a lengthier step. We have to run the PLL Mega Wizard because we want to tell it. We need 2 clocks. We need 1 clock for the CPU core, and we're going to use the Freescale 1-wire debug interface, which is known as BDM, which is going to talk through this thing. And it needs a slower clock. Well, it doesn't really, but it's nice to give it a slower clock so our little module can keep up with it. So we're going to give the CPU core a 40 megahertz clock, and we're going to give the BDM a 10 megahertz clock. And I think I could probably go up to, what, about 80 for the CPU? 160? On a speed grade 6? Yeah. I'm not going to push it. I don't need it to fall over. We'll be very conservative and give it 40 megahertz just for purposes of the demo. The clock that's supplied on the board itself is 50 megahertz, so we'll leave that alone. I know this is a speed grade 6 part, and I also know that this is falling off the bottom of the screen. How do I get this back? Good grief. I can't push the next button.
You guys got to come to sound check next time.
What's that?
That's when a rock band finds
I have
out
a
that the
problem here. I
equipment
can't-
doesn't work.
I can't resize this window, and I can't get to the bottom where the button is. Any suggestions for people who know Windows better than I do? I can't. There's nothing that gives me a resize, and it won't let me go full
Well,
screen.
minimize the windows, go to the desktop, and change
Yeah.
the resolution on the screen again.
And let it do what it does.
Well, I don't think that the projector actually adjusted this last time.
Yeah.
So if you make it
Ah.
Go all the way to the left
Go all the way to the left,
and click OK or apply,
and then do it again.
and then go back to where you were at 1024 by 768, and it'll adjust again. You can do it now.
Try 1280 by.
Yeah, it'll do 1280.
1280 by 768? The 768 was the problem. 1280 by 800?
Yeah, I'll bet you that'll work. Give it a shot. Now
If
it's
not-
adjusting. Now you see your PDF
Yeah.
Key Pro is at the bottommost part of the screen.
Yes.
Okay, it'll find that.
Yeah. Yeah, it's kind of scrolling left and right. We'll just have to put up with it. Okay, and we'll go back to SOPC Builder. Here. I still can't get to the button. There's still,
Try Alt space and F key. You may have to go all the way up.
all the way up to my full size and just let it wrap. Sorry. Yep.
Try to maybe resize the window, make it smaller.
You can't.
Okay.
No, it doesn't have a resize on it.
Maybe do 1280 by 1024.
Yep. Well, I'll just go to my full size. Oops, sorry. Settings.
Keep reporting 3 aspect ratio, not 16, right?
That's what this screen is. My screen is. I guess. Okay, but there it is, and I can click next now, and that's what I want. Okay, so that takes care of my clock input. Oh my God. Can you follow this? Okay.
It's actually very beautiful.
Okay, we'll take the defaults. And that's fine, we'll take the defaults. We're waiting to the point where we can actually blah, blah, blah. So here's our first output, the clock one. We're going to use this as the CPU clock, and we're going to set it to 40 megahertz. Let's just put 40 there. Everything else looks fine. Next, and we're going to add the second clock, and we're going to make that be 10 megahertz. Let's take the 0 out of there. Next. And I think we're done. Okay? Don't care about those. So when this is done, it's going to blast out this Verilog file, which is the part we're actually going to incorporate into the project. Okay? So there's that. Back to, and we'll finish. Now we have a PLL. Oh, you can't see it. Okay, here we go. All right. So here's our two components we have so far. We have a core and we have a PLL. Moving right along, we're going to add some memory, on-chip memory. We're just going to use some of the internal block RAM in the chip. You can't see that it says on-chip RAM. Can you see it now? ROM and RAM. And the first one we're going to add, we're going to let it emulate some ROM. Auto initialize memory, yes, yes, yes. I want this to be 8K. And I'm going to initialize it from a non-standard file, one that I'm going to supply, target.hex. And that's actually the output of the cross compiler. That's it for that one. One more for some RAM. Also 8K. We don't need to initialize this one because it's just RAM. Okay. Almost there. We need a couple peripherals. Microcontroller peripherals, interval timer, 1 millisecond timer. It's always nice to have a millisecond timer. Counter size is 32 bits. I'm not actually going to use the counter itself. I'm going to let it interrupt me. And I'm going to take just a simple periodic interrupt. Done. And then I want a PIO so I can talk to my actual I/O on the board. And then when we're done, we'll connect all that up. So we'll add a PIO. We only have 4 LEDs and 4 switches, so we'll make it be a 4-bit port. And we'll make it have both inputs and outputs so we can both read and write. Read from the pins and write to a latch. And that's that. Am I missing anything? Now we want to hook everything up. I want to see all the connections on here, so I'm going to set the filters to all. Now you can see all the interconnections. So the first thing we have to do is we have to take our memory mapped master, which is our CPU core, and we have to connect it to all of the memory mapped slaves. So this will take care of all the sort of memory fabric on the inside. You can see that we have the PLL as a slave. It has some registers in it, although we won't be using them. We obviously have to connect it to both of the memories. We need to connect it to the timer because it does have registers that we use, and of course the PIO because it has registers that we want to read and write to do our I/O. All that is memory mapped in memory space. We have to assign our clocks. Oh, you know what? I also took Lagoya's suggestion and rename these. So the input I'm going to call the oscillator clock, just so I don't get confused about it. And then I'm going to take the faster of these two and I'm going to rename it CPU clock. And the second one I'm going to rename BDM clock. Then I'm going to go down to these little pull downs and I'm going to assign all the correct clocks to all these guys. So the only place the BDM clock goes is the BDM. The CPU clock goes just about everywhere else. And you can see it's already there. The oscillator obviously supplies the oscillator clock. And the only place the oscillator clock goes as an input is to the PLL, and it does. The other thing we have to do is assign base addresses to these guys. I'm going to take the PLL, move it up out of the way. The boot memory has to start at 0, so we leave the ROM at 0. And I'm going to emulate the exact same way that if you were to go out and buy a honest-to-God 51QE128 Coldfire, its memory map would look like, since I know that I can match that. So I'm going to go in here. I'm going to change that to the default base address for that, which is 800,000 hex. It's a 24-bit address bus. And I'm going to put the timer someplace. Let's see. I have a list of these in the table. These are actually going to match up with the base addresses that I've assigned in the code. And here's that list. At the bottom of page 8 are the base address assignments. And the PIO. Actually, I want that to be, shoot, sorry, wrong one. Yeah. Let's say FF8000. Yep. Okay. That's that. I think everything's hooked up. So the final step to do here is to run generate. And what generate does is it takes this, everything you see here, and it blows out all the necessary Verilog files that will then be added to the project. Did I miss something? Yes. I did. It's actually, that's the right one. Yeah. And you know why. That's actually why I added the timer with an interrupt. There's a little bug in SOPC Builder that if you don't assign the interrupt, instead of driving all the lines, just pulling all the lines high like it's supposed to, it only pulls one of them high and leaves the rest of them low, so they're asserted, and you come up with all your interrupts hot. Not something you want to do. Okay. So we're actually going to assign an interrupt. So we're going to do generate, and if everything works well, any questions? This is a good time because this takes a little while.
What does the configurable version cost?
I think the license fee is 10K.
No, don't whistle at that.
That's
nothing.
not that expensive.
That ain't nothing.
No.
I could spend 1 year at University of California, Berkeley for that amount.
Not
Yes.
anymore.
No, you couldn't.
They had a food park last Thursday over there, the big
But
one.
when you're talking about the scale of this and you're replacing an entire part and you're going to make 1 million boards, it's cheap.
I don't know that you do 1 million
Well,
with this.
whatever.
Exactly.
The Coldfire said 16,000 circles, right?
The Coldfire is a descendant of the 68,000 instruction set, but it's a RISC processor. So What they've done is they've taken the 68K, taken all the really useful address modes away, and left you with a RISC core that's like a brain-dead 68K. So if you're used to programming the 68,000 and you've transitioned to programming the Coldfire,
You know some
you
of the instructions,
constantly
but
get illegal
they're the
instruction
ones you
traps. Yeah, that's right. What do you mean I can't add a byte to that? Because you can only add a long word to that. So, did we get successful? Yes, that's the line we want to see. The bottom line, system generation was successful. We are done. So we will say, oh, we're nowhere near there yet.
No, but it's an
Okay.
accomplishment.
It is an accomplishment. So we'll say yes to save our top.sopc because it made a few changes to it. We're going to go back into Quartus. We're going to add those files in that it just generated. I really wish it would add them itself. You'd think it could do that. Project add remove files. And they are luckily up at the top level, so they're easy to find. So we're going to add the PLL and the top. Oops, sorry, there's a way to do this. PLL.
Control.
Top, yep, exactly. Clock, because I don't want them all. I don't want this one that says top inst. And the memories, and the PIO, and the main PLL, and the timer. I'm going to add them all to the project. Cool. The next step is we have to run the analysis and elaboration step, which does two things. It checks the design, so if anything blows up or is just really wrong, it'll tell you. And it also figures out where all the connections are, because we have to actually take those internal connections, those internal nodes that were generated for the PIO and for the BDM wires and for a reset line, and we have to bring them out to the outside to actual physical pins on the part. So we'll make a quick pass through that and assign them. The design files that come with the board comes with this enormous spreadsheet that lists every one of those pins on the part, all 324 of them, and tells you where they go. We only luckily need a few. So we're just going to connect up just the PIO pins. Only 11 warnings. That's cool. So we're going to quickly go over here to the assignment editor, and we're going to make those assignments. This is another thing that doesn't want to fit. So here in the to field, we're going to actually go into the node finder, and we're going to go grab, you see here, I'm going to look at all the pins, and I'm going to tell it to list them. And here they are. And the ones I want are background, BDM clock, BDM reset. I don't care about CPU clock, that's internal. I want these 4 PIO bits, and I want these 4 PIO bits. And I also want, where's that reset line? BDM reset in. Oh, I got it. POR reset, sorry. And I will say OK to that, and all those pins are going to show up on the list. I also want to take the BDM lines and put some pull-ups on them, because without them, they're just sort of floating around and will do bad things. So once again, I'll make the list. I'll go grab those 2 lines. Those 2. Yep. Okay, so there's all my pins. Now I got to do something with them. I'm going to take the pins and actually assign them to locations. So I'm just going to go down this list and quickly say location for everybody. We'll come back and put the locations in at the end. And for this one, we're going to say weak, weak pull-up. And then we'll go back to the top of the list, and I have the list here, I hope, in the right order. Nope. Oh, no. Where's OzClock? I'm missing one. We need the oscillator clock, or we're not going to get a clock in from the outside world. Location, pin, V9. Somebody wants to read these to me. Background to and from the CFE1 core. Oops, really? And E1. Okay, BDM clock.
F3.
Oh, wait.
Oops, no.
I don't actually want that one, do I? No, I don't need it. I actually, yeah, when I made the list, I really wanted oscillator clock. Okay, BDM reset in?
Yeah,
3. Thanks for the help. Import 0.
F1,
Import 1.
F2, A10, B10,
And then all the out pins.
P13,
P13.
yes, P12, N12, N9,
POR reset.
N2,
Yeah, sorry, these aren't in the same order. Pin. Oh, yep. On. Am I missing a pin? Okay, on. Good. Okay, done. Now, what's the next step? Build. Right? Okay. Now we compile the whole thing. This takes 6 minutes. This would be a great time for questions,
So,
discussions,
the
gossip.
thing that you're going to download in terms of software is SwiftPort right off the...
Yeah, I actually made a list.
SwiftX
I made a
right off
list.
the shelf.
Yeah, I made a list at the beginning. It says getting started.
Yeah. If I were to buy SwiftX for this processor,
Or use the demo version, because I will make it so it works with the evaluation version.
cool.
Where is that list?
But let's say I wanted to do actual work and
Yeah.
sell it. I'd need to buy it from you. How much would that cost?
It's, I think, $10.95. Maybe it's $12.95. Something like that. It's the SwiftX Pro version with the optimizer. That's $12.95. $95, not $12.95. That's
I was
correct.
thinking 12,000.
Oh, no, 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 no. It's $1,295. No, 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 no. That would be $12,950. That's correct. You could certainly use the Cordis Web Edition to do all the rest of this, and that's free. If you get the subscription edition, I'm not sure what extra good stuff you get with the subscription edition. You can do incremental compilation, which would be a great saver, as opposed to having to do this all the time.
Need a make file.
No, you don't need a make file.
Sorry.
So, it's still cranking away, compiling. When,
setups that every time it powers up, it sucks it like a pig from a little nut ball?
you can do that by taking the result of this and programming it into the flash that the device boots from. I'm not going to do that. I'm just going to download it. Yeah, the two connections that I have here to my computer, one, there's a JTAG port that goes to the Byte Blaster, which is Altera's JTAG interface. That's going to actually blow the configuration into the FPGA directly. That same image, I believe, can just be programmed into Flash, possibly with a little wrap around it, so it loads it directly from the Flash chip. Right now it does, yes. Yeah. The one that's already in there that was pre-programmed on the board. But this could become the one that's pre-programmed on the board. Yeah.
But yes, it sucks it in from another part rather than from the laptop.
Yeah, it's right, correct. Yeah. So the one that's in there is their demo, and in fact, it's called My First FPGA, and that's the little tutorial that you run when you first get the kit. And so I did that as my first tutorial, and it took me a while because I've never worked in this environment, and oftentimes I would scratch my head and go, "Why would you want to do that?" And then, of course, being a newbie, I'd look at some of these menus, like this one that says Processing Start. And all of these things pop up that you can start doing. I don't know what half of that stuff means. Maybe two of them that I use. But somebody somewhere uses them.
Start classic timing analyzer.
Yes.
That's the same one used by the ancient Greeks.
The classics, to time how long it takes to read them.
That's what classic means.
One of the reasons I chose a relatively slow CPU clock here is I don't have to apply timing constraints, because that's another whole layer of stuff that A, I don't know how to do and make a reasonable decision about, because I know software but I don't know hardware. And B, it just takes a lot of time. Yes? There's a report that comes out at the end that we can actually go in and look at that shows you the percentages. The Cyclone 3 is a fairly modest part. It's not like a real, big fire breather, but it's relatively small and also cheap. And I think we're using, about a third of it?
The cycle through on that board is 25,000 watts, and the CPU is about 6.5.
Yeah, it doesn't, I couldn't find a breakdown anywhere saying how much of it was CPU and how much of it were the extra elements I added on. So I can just see the total usage. And it seemed to me that in terms of the LEs, it was using about just under a third of it.
Do you know if this is going into outer space or what?
What?
What NASA's going to use this for?
Their ultimate goal is to have a kind of standard component that they can build on, that they can fly. So one of the goals is you want to have as few parts as possible, and of course it has to go into something that's rad hard. And I think their favorite rad hard parts are Actel FPGAs, and I don't know the reason for that, because that's sort of not my world, but I know that they like them. And Ting, you missed the beginning of this. This is all from Robin King, who sends his greetings to you. And Robin has been trying for years to get something that he can drop into an FPGA core. And of course, you know, you did, which was the one that you did for them? The F32 or something? EP32?
Was that stereo, Ting? That flew on stereo?
The stereo is a 24-bit configuration.
Okay.
But Robin King wanted 32-bit.
Yeah.
He wanted
Right. So this is a 32-bit processor that people at NASA already know and love, so he can actually get some buy-in from them to do this, even though it's enormous compared to the EP32. It has a huge footprint compared to that.
It's a very small club that have flown their processor architecture in space. Ting and
We-
you could say Chuck was the progenitor of the Paris RTX.
Yeah, and there's a lot of them up there. There are.
There's a lot of RTXs up there.
Yes, there are.
And to this day, they're
Yes.
still launching.
We did a project for a company here in the Silicon Valley about 6 or 7 years ago that was to be put into a satellite, and they decided that they would take an 8051 IP core and put it into an FPGA, and the goal was that they wouldn't have to have a separate CPU, although there were rad hard 8051s. I think there still are. UTMC had one. And the goal was to get it all into one chip, because most of the science that was being done by this, which I think had to do with some sort of atmospheric gas analysis or something, was in an FPGA. So the whole goal was to get it all into one part. Well, it turned out that that 8051 took up so much of the logic that then they needed 2 of them. 2 great, big, fat, expensive rad hard FPGAs, and they were so far into it by that point, they just had to do it. So it was an interesting exercise, but they really could have just used an 8051.
That is the preferred target for this is Actel.
I only preferred, or I'm only using the, NASA's preferred, they like the Actel rad hard parts.
Which doesn't move from flash, it is not level.
That is correct. Yes.
So how would you get
More like an ASIC.
from this to a chip from another FPGA?
I don't know.
At the beginning, when you tell it what chip you're generating,
No, because Quartus is an Altera tool, and I'm using the Altera tool chain.
Yeah,
If
but
you were
you're
doing this for
generating-
Xilinx, you would use, the Xilinx EDK, I suppose, but you'd have to wrap your own Verilog around it to pull it into their memory or their internal bus structure. There'd be a bit more work to do. The really cool thing about this is that because this is brought out as to the top level as an SOPC component, you can do all this, just drop in and make the connections thing, as opposed to having to build all of your own logic, all of your own Verilog around it to make it go, which is what they will have to do when they put it in the Actel.
I think the great part is that so much of it is human,
Yeah.
and software guy like you or me.
Yeah, an idiot like me who's never done this before could basically bring the... Now, my first few tries were failures, but I learned a lot along the way. But I mean, I've got it. I can crank one of these out in about 10 minutes now, except for the compile step. Which, is it done? Yes. No.
Like it is so fantastic. You're
What does that say?
talking about a whole PC board and everything.
51%. Oh, man, this is long.
72%.
Did it just jump to 72%?
Yeah,
Oh,
maybe
it was...
It likes to be looked at.
Wow. Well, maybe that's it.
It's an attention whore.
Either that or the...
It's gonna pop. Boom.
that guy who did the Windows file copy dialog was here. Did you see that cartoon? I'll be there in 6 minutes? No, 2 days. No, 30 seconds.
XKCD.
Yes, it was. Did you see that one?
I did.
The guy who wrote the Windows file copy dialog goes to
Where
visit
I
friends.
followed that,
Yeah.
I was walking down University
was good.
I've seen a couple.
Hey, it was
KCD
successful and
t-shirts.
only 49 warnings. And most of these warnings have to do with things that we don't care about, like timing constraints. So we don't even need to look at them because there were no errors. So we're good to go. So the final step here is to take this and actually program it into the device. So I'll use the shortcut to the programmer.
Why do you need clock uncertainty?
You don't.
It's really stressed out about it though.
No, it's not. If it were stressed out, it would have given you an error and it would have refused to make it an object file.
Well, that's like me going to work. and
If
saying,
we
"I'm
were
not gonna
running
do
this
that."
really fast, then we would apply timing constraints and we would run a timing analysis on it. We're not going to do that.
All right.
Because two reasons. I don't know how, and we don't have time. So on we go. So here's the actual output of all of that, and this SOF file is going to be blown over by the byte blaster and the JTAG, and it's going to end up inside the FPGA, and it's going to run. The image of the target compiler output was that file target.hex. Oh, I didn't actually put that in here. Oh, crap. We have to do it again. And Blagoya mentioned this when he read my app note. He said, you really have to make a point here that you need the SwiftX file. So we have to do that again. It actually programmed it with a blank memory image. And it does an error on that. So over here in the SwiftX project, notice how big the CFV1 project is in the Altera. It has all of these files and subdirectories in it. And then we get over to the whole fourth system, and that's all there is. And one of those is its object file, which is target.hex. So we're going to have to take that, drag it over to CFV1, and we're going to have to compile again. Sorry. I got too excited and I skipped a step. Okay, well, while that's running, any further discussion on that?
So are you queued up to?
How much flash do we need to configure the FPGA?
Oh, the same size as that SOF file, which I think it's probably deleted because it's making a new one. When it's done, let's look at how big that is. Oh, here's one. 680K. That's sort of consistent with what you see like in a Xilinx part when you take your top bit when you're done, and it's 600K or a megabyte. It's similar. And it's tiny compared to what a flash chip holds, right? I said that's a tiny portion of what most modern flash chips hold, so not really a big deal.
So if the flash though is a serial port flash, then
Like an SPI flash?
yeah, okay, so if you get the SPI cranking at 10 megahertz, then it would take 70 milliseconds.
To configure. That's fine for startup, because you only do it once. Any other questions? While I'm wasting all this time recompiling because I skipped a step?
Are you queued up to fly on a specific mission, and if so, when's that?
No, this was just a proof of concept when we did this. We did this just this last September, a few weeks ago. So the next thing now is to, I'm not quite sure what Robin's next step is, but he now needs to elaborate this and actually build a whole sort of foundation platform out of it that people can build their projects on top of. So playing the game at NASA, he has to get more funding to do that. You know how that goes. Yeah. I'm not an FPGA expert. I'm pretty neutral on them. It's a relatively modest, cheap part. Seems to work fine. Most of the projects that we do that have FPGAs use Xilinx parts because we do a lot of telecom stuff, and their IP for telecom is good. So we're mostly doing Xilinx stuff. What's the percent? Oh, sorry, we're not watching. Ugh. All right, 35. I think this is the point where it starts to speed up.
If you look at it, it goes faster.
Really? I thought a watched pot never boiled. Not so.
But you got a warning.
Oh, well, we're going to get lots of warnings.
That's the Heisenberg uncertainty thing.
Yeah.
You know, if you look at it with a megawatt laser, it'll boil real fast.
Sure. We can look at the warnings window while they're accumulating. A couple of them are critical warnings, and again, they're not all that critical. Synopsis design, don't care. Clock transfers, don't care. Not so bad.
It's one of the many advantages of high-power LiDAR.
eventually when we get this done, and if I didn't make any mistakes, we'll program the chip, it'll come up, we'll connect to it with the interactive debug interface and actually finally talk some forth to it. Yes? Target.hex. And the hex file really is kind of like the hex files that you've known and loved for 25 years from the old Intellect development systems. What? You want to see?
So it's only limited, it will only do 64K?
No. It's in long words, and it's a long word address.
So it's not the same.
Altera, I'm just going to quickly compile one because I can't find it. There, that's a lot faster. Yes. Yes. Yes, except that Altera has done something a little funny. If your target memory is 32 bits, the address field is here is assumed to be a 32-bit address, not a byte address. So it's non-standard. It's not really a hex file, even though it's the exact same format. That was one of the challenges that we had to overcome because our standard output is standard Intel hex. So when you try to burn that in, what you end up with is a memory map full of holes. So I had to make a modification of the cross compiler so that it knew how to do 32-bit wide object files to output. Okay, so we're ready to go finally, and we'll do a program. Got the programmer? Yep. Select the SOF file, say start, it should just blast it over. So for some strange reason, it always puts itself in the background so you can't see what it did. But it's successful. And then we'll connect here. And voila, we have a connection. So what we did here was I clicked on the little debug button, which actually includes a file called debug.f that establishes a connection through the debug interface, which you can just think of as a serial port. And say again? That's BDM. BDM, Freescale's, it stands for background debug mode. I don't know why, but
Bloody debugging module.
bloody debugging module. I often quote you on the need for a debugger, by the way. There's two different versions of it. This core uses a one-wire BDM, a very simple one. It's the same one that they use on their HC12 parts and their HCSO8 parts. The fatter cold-fire one, the V2, 3, and 4 cores, has lots more pins and gives you a lot more information in real time, but this is fine for what we're doing. So this very last thing you saw it do here where it output this string, blah, 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 that's actually the target sending a message back to us to display that message in the debug window. It's a word called greet, and if we look at it, we can actually just assemble it. So there's the actual code for greet. And I already have some words. They have LED in them. Yep. So I have some words to initialize the LEDs. That makes the output port be outputs. And then I have some words that actually write to them. That's not what I expected to see. I'm writing to the LEDs. Hold on, let's see what that looks like. So I've wrapped up a little application around that just does something. Let's pop that up in the editor and have a look at it. So I made this little demo program. Good grief. Okay, can we see the actual code now? There we go. So store LEDs just writes out to the PIO base. Slash LEDs just puts nothing there to start with. And then I have a word that ultimately blinks the LED once for 100 milliseconds and delays 100 milliseconds. Does that all make sense? And then I have something that runs and shifts a bit along and moves it in one direction and then moves it in the other direction. And then I have a background task that I'm going to assign that to, and I say, just go ahead and do that. And at the very end, here's the whole thing. So let's see if it does it. And sure enough, there it is. Yeah. All that prep for a little light show.
Yes, but it's blue lights.
Very trendy. It's the blue light special, the walking blue light special. If we wanted to read it, because I gave that to a background task, we haven't busied our task that we're connected to here with other stuff, so we can still do stuff with it while it's running. One of the things we could do is what is that thing called, PIO base? I copied these out of a .h file. I hate underscores. Greg Bailey once told me how you pronounce them. So there's the, let's see that in hex, it's more interesting. So there's the contents of PIO base. If you just read it in, if I push down, I don't know which end's which, but if I push down one end, I should see it go away. Sure enough, there's the other one, and the other one, and the other one. So I could presumably wrap some code around making tests for those buttons being pressed and then do something like blink a light based on the button. And if I had had time, I would have done that, but we're just about out. My guess at 50 minutes is pretty darn close. Okay, now any questions on the fourth part, the good part?
How big is the actual port image? Roughly.
How about exactly? This word.allocation displays all the various memory sections that I've allocated, and I have a code section called prog, short for program. I can't call it program because that does something else. And, oh, let's see that in decimal. So I've allocated, remember I allocated 8K apiece for ROM and RAM, and my ROM section is 8K, and I've used 6,342 bytes, so I have 1,850 left. That's not so bad. And that's everything. I mean, that's the multitasker, an entire core word set, everything. It's 6,342 bytes.
That's bytes.
Bytes. Bytes. Yes. Yeah, I still think in bytes, sorry. If you want that in long words, get out your calculator and divide by 4, and you see you have a remainder of 2. And then I have a little section there called PRAM for program RAM, and that's all the code we just wrote to do this application, instantiate a task, run the loop, and so on. And you can see that it is 150 bytes. So there you are. And I know people think that these days memory is free and cheap, but when you're operating in a constrained environment like this and you only have a little bit of block RAM in there, guess what? You have to tighten things up again, and it's already done for you. Questions? No. Anyone still awake? Yeah. All right. Okay, I've ended early. Excellent. I will correct all the embarrassing mistakes in here and post an update, and I'll post the source code for this project with the update, and it'll be in a zip file on our homepage by Friday. Yes, I'll be working on Thanksgiving.
And give